Hello, everyone, and welcome to the G2M Research webinar on responsive and efficient storage architectures for cloud service providers. My name is Mike Human. I am the lead analyst at G2M Research. Let's kind of go through the ground rules a little bit on the webinar. This is our agenda here, so I'll spend a little bit of time talking about the different ground rules of the webinar and introduce the topic. Then we'll have each of our three companies talk a little bit about on the subject, and then we'll have three panel discussion questions. We'll also have a couple audience surveys that will be wound into that. And then finally, we'll finish up with audience Q&A. If you have a question, please use the Zoom Q&A window to submit the question, and then we'll hit those at the end of the webinar. Also in the polls, those are also done through the Zoom polling window. And we are recording this webinar, and a link to the recording as well as the slide set will be made available to everybody who registered. That should go out no later than Thursday this week, so you should see it in a couple days in a separate email. So let's talk a little bit about cloud service providers for a second. So, if you think about hyperscalers and cloud service providers, obviously a variety of different scales of organizations here. But they have some very unique challenges. If you think about hyperscalers particularly, they store roughly half of the world's 1,000 exabytes of digital data. So that's across maybe a handful of guys, and under 100 data centers are holding all this data. It's not uncommon for these different data centers to have a terabyte per second of bandwidth. Even in CSPs, that's oftentimes, if you think of somebody like Facebook or a Netflix, that's not uncommon. They also have millions of concurrent users. So if you think multi-tenant operations, these are hundreds or thousands of times bigger than that, and they're spread over geographically dispersed data centers. So you've got a lot of coordination you have to do across them. Some of the things that CSPs and hyperscalers look for when they build up these data centers and when they look for the hardware looking is ability to rapidly scale the number of users, bandwidth, and capacity, right? One of the reasons people use the cloud is they can grow their operation and their footprint rapidly and shrink it down as necessary as well. So for a CSP or a hyperscaler, being able to rapidly and easily do that's critical. It's oftentimes the difference between winning a new customer or not. They also want to minimize CPU utilization by their infrastructure, right? CPUs to them are something to be rented out. The time on those is used. That's what pays the bills. So, if you have drivers and things like that, they're eating up lots of bandwidth. That's not a good thing. Minimizing the power footprint. Most of these guys are very, very, aware of the power they use in their data centers. They're taking big steps to reduce the power either from cooling or electricity. So minimizing power footprint's important. And finally, being able to provide predictable end user performance. In most cases, a hyperscaler or CSP might not give you the best possible performance you could potentially achieve, but their goal is to make sure that the performance that you do get is consistent and predictable, even in the face of outages or other things that can affect availability and resiliency. So with that, let me introduce our panelists. Our first panelist is Kirill Shoket. Kirill is the Chief Technology Officer at Accelero. Next, we have Steve Fingerhut. He's President at PlyOps. And finally, Rob Davis, Vice President of Storage Technologies at NVIDIA. And with that, let me go ahead and Kirill, pass the screen to you. All right, you should be in control now.
Okay, thank you, Mike. Thanks a lot for the opportunity to present our solution to such a wide audience. Good morning, afternoon, or evening, everyone who is on this webinar. So without any further delay, I'd like to get to the business. So, okay, little bit delay on the slide side.
Here we go.
Okay. So what are the defining characteristics of CSP operation? There are many, and some of them Mike mentioned, but I think that these four are very important, especially when we talk about underlying storage infrastructure. Agility means that CSPs, for CSPs, there is no way to assume anything about an application stack running on a node or in a rack. Unlike, let's say, HPC environment, where we know that bandwidth is super important, more important probably than latency. So CSPs need to be prepared to run efficiently any application, from transaction on the database to distributed file systems, and run them in any place in the data set. And efficiently is actually the key here, bringing us to the second point. CSPs are there to make profit, while competing with both public clouds and other CSPs for customers. So CSPs are already operating at razor-thin margins. So if a competitor is able to more efficiently use the same hardware resources or use newer hardware to run the same workload on a smaller footprint, it will beat you on price. And the third point is actually a direct derivative of success. The more successful CSPs, the more scalable operation should be, and therefore the more efficient it needs to be. Scale punishes any design flaws. And actually, the last point is super important, but it's also obvious. No one will use a cheaper service if it is unavailable sometime. Okay, not a short amount of time. So how do we, once again, so how do these characteristics apply for storage infrastructure? Agility is pretty straightforward. Storage infrastructure needs to satisfy the needs of any workload in terms of bandwidth, either per seconds or latency, and all of them are equally important. Efficiency, let's say a CSP wants to cater to a modern AI training workload and to deploy NVMe drives or newer PCIe Gen 4 systems like DGX boxes or something like that. They are expensive. Any new hardware is expensive, but it's also much more efficient. It provides much better performance density, so you can run the same workload on a smaller footprint or run multiple workloads on the same footprint. But you need to be able to extract this efficiency from the underlying hardware. And this actually brings us to the combination of these two properties, which means that storage appliances with their long hardware cycles and siloed deployments just don't allow CSPs to run an efficient operation. It took us, for example, you can see here on the right-hand side, it took us several weeks to optimize our software to PCIe Gen 4 and extract full performance of the underlying drives and networking. And at the same time, some of our customers were already getting the new hardware for POCs. It takes appliances up to years to actually use the same hardware in their underlying systems. Scale in the storage world is probably the most frightening aspect because it involves storage networking. And developing a production-grade storage networking, which is both robust and efficiency preserving, it's just hard. And scale means we get into resiliency of distributed systems. And in distributed systems, people usually take a lot of time to design distributed data paths, but forgetting the control paths when dealing with this resiliency is very easy, but fixing it afterwards is really, really hard. Next slide. Okay, so if we were building a CSP storage, what it would look like? Without any particular order, we can start with the client side, the application-facing part of the solution. It better be as invisible as possible to be able to work with any application stacks as possible. So application VMs fail. They fail because underlying hardware fails. They fail because applications fail. So for overall resiliency and application mobility, it's much easier to handle stateless storage clients where all the state is stored actually on the target side. Now to the east-west traffic. Avoiding it not only makes networking easier. No east-west traffic actually helps storage with both the resiliency to client failures and the handling of heterogeneous hardware. CSP infrastructure usually consists of different hardware generations. It may be different networking, different processors, and so on and so forth. East-west traffic leads to lowest common hardware denominator, which constrains the overall performance and reduces software the solution efficiency. The control path is actually maintains current truthful representation of the system. So any failure, any error there is really critical. But errors and failures happen, and we need to embrace them. So cell-based design of the control path helps to contain these failures and not to propagate them across a data center or data centers. And finally, talking about data path offload, it's actually relatively new compared to other parts of storage architecture, but it's a very hot topic since we know that CPUs are really bad and inefficient in handling of a lot of fast I/O. So getting CPUs out of the data path, especially at the focal point of the operation, which is target side, is very important. Obviously, the hyperscalers, with all their means, solve this in-house. But their solutions are out of reach for the vast majority of CSPs until now. So from the commercially available solutions, Acceleros NVMesh, with its client-side distributed architecture, has all of the characteristics presented on the previous slide. It has a stateless client, which can move seamlessly between VMs. It has no east-west traffic. The NVMesh control path is highly resilient and cell-based. And in addition, we have NVMesh protocol, which is both scalable, production grade, and is able to bypass target CPU to achieve really groundbreaking performance density at scale. So are we there yet? Is this ultimate solution for CSPs? Not 100%. Why? On one hand, client-side NVMesh is just a kernel device driver which fully mimics standard NVMe device driver, but still it requires installation of third-party software on the application side. And in many cases, this is something that CSPs are really like to avoid. So is there a way to solve it? Yes, with data processing units, we can offload this client side to a smart network card, preserving all of its properties, but without actually installing any third-party software on the application servers themselves. We already know how to bypass CPUs. So we have a really good performance density, and there is no noisy neighbor between various workloads actually competing for the same CPU resources. But on the other side, we still need memory bandwidth on the target side for bounce buffers, for all kinds of memory-related operations on the of the storage infrastructure. So what the upcoming CXL protocol allows us is to fully bypass CPU's memory complex as well, which will bring the overall efficiency to a really new level. And finally, there are features that shouldn't be on the client side anyway, because they are very much data dependent. For example, compression, encryption, and so on. So how to handle them without wasting client CPU cycles? This is actually where hardware accelerators come into play. And when these hardware accelerators have an NVMe interface, they are actually, they allow NVMesh to control them same way it controls standard NVMe drives, and seamlessly introduce these advanced features into the overall operation. That's all from my side. Thank you.
Thank you very much, Kirill. Let me.
Yeah, I will give up remote control. Okay.
All right, and next is Steve Fingert. Steve is president and CBO of PlyOps. Steve, you should have control now.
Great. Thanks, Mike, and thanks everybody for joining. And Kirill, that was a great introduction, a great setup for PlyOps, so appreciate that. I want to talk about, obviously, we all know about the huge data growth that has been talked about, right? The zettabytes being created and stored. More and more of that is being stored to flash. Since 2015, the amount of SSD shipped has grown 6x. And by the end of this decade, it's expected to grow another 40 times more. So we have a lot of data. We all want to access it very quickly. We're spending a lot of money on SSDs compared to hard drives. And the question is, how do we make that happen efficiently? So we want to talk about some of the challenges with this broad SSD adoption. First, the server architectures are not balanced, and that applies to storage systems as well. A hard drive on a good day can deliver around 200 IOs per second, IOPS. A pretty bad SSD would easily deliver 1,000 times that, and the good ones these days are even higher than that. So you have your media has just increased in performance by 1,000 times. None of us are getting that type of scaling from our application. So where is that performance going, right? The server has not kept up. The way that software, like databases, software-defined storage file systems, the way they try to keep up with that and deliver higher performances, they have to cut corners. And the way that shows itself in the system is they're amplifying the data. They're not compressing and packing as efficiently. They are using the disk as a scratch pad, and that amplifies the amount of data read and written to those SSDs, which can wear them out, can consume performance that you would use for your application. And if you're doing this over the network, it will consume very precious network bandwidth. And also it consumes more space on your disk itself. So you're spending more money for these expensive SSDs because your application is trying to keep up with the performance. And then the last major barrier we see is system reliability. So, even with distributed architectures that you see, both file systems, software-defined storage, whether it's integrated into the application, like in many databases, you still benefit from your local node being more reliable. So we talk to a lot of customers. They're using RAID 0 and their local server nodes. They're using HA software or cluster software or distributed erasure coding to keep those, you can survive failure. But those failures are very expensive, right? You might have a service outage, you might lose some, short amount of the data during the transition, and then the rebuild process is expensive from resources, and your system performance overall degrades during those periods. But really the choice is you either go to RAID 10, which is mirroring and very expensive, or you go to RAID 5, which is just unacceptable, right? Nobody uses RAID 5 with these very high performance NVMe SSDs because the performance penalty is just too high. So these are all issues that the industry needs to deal with as we greatly expand our use of flash in the data center. And PLIOPS is addressing these. So we have our PLIOPS storage processor, which is delivered as a low profile card, fits into any standard server. We'll talk about accelerates any workload that runs on flash, works with any SSD. We're not selling the flash, work with all your current favorite suppliers. And we deliver value on 4 vectors. Number 1 is reliability. As Kirill talked about, right? That's table stakes. And we can deliver what we call drive fail protection. We don't want to say RAID 5 because it has so many negative connotations, and we actually have a different architecture. But the ability to survive a single drive failure, continue operations, rebuild automatically, we can deliver that with twice the performance of RAID 0. So there's no compromise to delivering that drive fail protection. Performance, we'll see, from a 2x up to either 15x or higher, based on our unique architecture. Capacity, you can store up to 6 times more user data on your SSDs than you can with software solutions alone. And Kirill also spent a lot of time talking about the importance of efficiency. We totally hear that from our customers as well. And one way we're helping with that is we can use the lowest cost SSDs. So TLC, 3 bits per cell is what's commonly used today in SSDs, but there's a new class of QLC, or 4 bits per cell. It's significantly cheaper. The problem is it's very sensitive to writes, and you have to manage those very carefully. And with the PLIOPS solution, you can use either technology with the same performance, and you don't have to worry about endurance. This shows the diversity of applications that PLIOPS can work with. This is really just a representative example. There are many others, but really these are the applications that are used on flash today. Right? You have different databases are big consumers of flash, so both relational databases and NoSQL. Analytics, of course, you want the fastest access to data, and more of those are being put on flash. And then finally, software-defined storage, distributed file systems. We're seeing a lot of interest here, and these are, once again, just a few representative examples. And that's where a lot of bits are being stored. And to see how this fits in, and Rob will talk more about some of the advanced architectures that can be achieved with the NVIDIA technology. But if we look at this from an evolution, I call this yesterday's model. It's actually being used a lot today, or predominantly today, which is you have your processor. It's a very compute-centric world. Everything is done on the CPU. You have storage and that's managing control of the network. Really, where things are moving today is that you have a dedicated storage processor to, as Kirill mentioned, right, to have those hardware accelerations to achieve the types of efficiencies that are needed to continue to scale. And you're bringing in more data-hungry applications like AI and ML, which are running on GPUs. And really, with this setup, you can multiply the performance, reliability, capacity, and efficiency that's available to the application. And then as we're moving forward, we see a lot of use. This is actually being started to use today, but we'll see this rapidly expand in the very near future, which is the use of the DPU, or data processing unit, that NVIDIA has offered, which really manages the traffic and improves the isolation. As Kirill mentioned, if you're a service provider, you want to have all of your cores available to sell or to rent, and that's how you make your money. Bring all of that, as much overhead into a offloaded device. Now the DPU and PLIOPS storage processor will work together and accelerate that storage management. Now, just simply moving it from one processor to another doesn't change the architecture, doesn't change those challenges that I talked about, and we can work very well with the DPU to accelerate those and deliver the types of efficiencies that we're talking about. And this really becomes more of a data-centric view of the world instead of a compute-centric. Of course, compute is very important. Will continue to play a huge role with managing applications and want those to be free to do more of the type of work that they're best at. All right, and this shows some representative workloads and the actual performance scaling on the left. So compared to software alone, and this is showing compared to a RAID 10. So very high performance, but very expensive storage solution. And even with that, PLIOPS can deliver these types of multiples over a software-based solution. So you're getting both the performance scaling as well as the efficiency, the reliability, and the greater expansion. You can see how that on the right, that shows how that manages or how that works out from a TCO savings perspective. So easily getting over 50%, and depending on your environment, these can go even higher. And just to double click on that, at least one example, and show how this works in a real customer environment. So we have a customer who's a large e-tailer. Many of you are quite familiar with them. And they had a current solution where they were using basically 3 servers to achieve and this is just a microcosm of the larger scale, but in a given pod, they had 3 servers to achieve the performance and storage goals, which you see at the bottom, 150,000 queries per second, around 31 terabytes usable in a RAID 10 configuration. With a PLIOPS accelerated solution, you can deliver more, essentially the same performance, but with 1/3 the servers, 58% more capacity, and with very efficient high performance dry fail protection. And in this case, the customer saw over a 50% drop in CapEx. This doesn't count all the power savings, everything else that'll be so important to all customers, but just shows the tremendous efficiency that can be gained by using the right product for the right challenge. So key takeaways here: with the huge growth in data, the huge interest in using SSDs everywhere to take advantage of their performance and reliability. But those are great trends, but they do require a new approach. The PLIOPS storage processor multiplies those TCO benefits to make that more scalable and cost efficient. And you can please learn more at pliops.com. So thanks, Mike. Back to you.
Thanks, Steve. Next up, we have Rob. Rob is the VP of Storage Technology at NVIDIA. Rob, let me pass you control. And to answer one question that one of our people had, this is being recorded, and we will make a link to that recording available to you. That you should get an email on Thursday. All right, Rob.
Thank you, Mike, and hello, everybody. And thanks, Mike, also for inviting NVIDIA to be part of this webinar. So how are we going to connect up all this awesome technology Steve and Krill have shown us for cloud service providers? And most importantly, at the same time, maintain the performance. If I can figure out how to change the slide. Mike, are you sure you gave me control?
Looks like you're moving around the cursor. So here, I can forward for you if you like. There we go.
Okay, weird. Okay, so let's start with the basics. As Steve said, SSDs are taking over the world. And the SSDs are really the root of both of their solutions, and SSDs are what have changed networking storage. The reason is because storage has gotten an order of magnitude faster with the move from hard drives to SSDs, as Steve pointed out. This chart shows the number of hard drives needed to fill different network speeds. You can see that 24 serial ATA hard drives, which is a common number in starter all flash arrays or JBODs, is a good match for 10 gigabit Ethernet. And if I can get it to move to the next slide. Wow.
It says you're controlling it. Try clicking again, see if that does it.
Yeah, I've clicked multiple times. There it goes. Okay. But now look at the difference when we look at NVMe SSDs. It only takes 4 to fill 100 gigabit, and a PCIe, and think about this, you've got, those are Gen 3 PCI drives. So we have Gen 4 drives coming to market this year. Actually, multiple vendors have them already. And in a few years, we're going to have Gen 5 SSDs. Fundamentally, SSDs move the bottleneck for network storage from the storage to the network. Fortunately, at NVIDIA, we make really fast networks for both Ethernet and InfiniBand. We have 200 gigabit Ethernet and InfiniBand adapters, switches, cables, media modules, and DPUs today, with 400 gigabit on the way next year. Our switches already support 400 gigabit inter-switch connections. But faster wires is only part of the problem. This graph shows the relationship between the performance of the storage media and both the networking hardware and the networking protocols. Because we also need faster protocols to go with the faster network speeds. That's because as the storage media gets faster in comparison to the network hardware performance, we can't forget that we need more efficient protocols running on the faster wires, like NVMe over Fabrics, for example, and more importantly, RDMA. RDMA is the remote version of DMA. This is direct memory access. It's a hardware-driven transfer of data from memory to memory within a computer system. RDMA is the remote version of that. It's the networked version of this. It's a hardware-driven memory-to-memory transfer across a network performed by InfiniBand or Ethernet adapters on either end. Instead of the network transport layer being in software like with TCP, with RDMA, it is in hardware on the network adapter. So you get lower latency, higher bandwidth, and lower CPU utilization than you would with TCP, with TCP as the underlying protocol. RDMA was developed for high performance computing on InfiniBand, but has now moved into the mainstream Ethernet market with Rocky, RDMA over Ethernet. This is running under common storage protocols across all categories of storage today. NVMe over Fabrics has definitely helped to drive this move into the mainstream, but RDMA is now supported in-box on all 3 of the major operating systems. And many of the hyperscalers publicly acknowledge they use it. And if you follow some of the acquisitions the others have made, you might guess that most of them do as well. And RDMA is also a requirement to connect network storage to GPUs with NVIDIA's new GPU direct storage technology. And for networking persistent memory in a data center, RDMA is really the only choice. There is some perception in the market about Rocky being hard to use, but much of that comes because it's new, and that is a typical reaction to the unknown. It also depends on your network adapter and switch vendor's management automation level. At NVIDIA, for example, it takes one command to the Ethernet switch management to configure for Rocky. And we have recipes for most of the other vendors. We support these three approaches. ECN only, which is a switch setting that enables it to set a bit in the data packets flowing through it when its buffers are almost full. This bit tells the adapters on the data path to slow down their transaction speeds. You can also add PFC to this, which is a command the switch sends to an adapter if its buffers are full and it can't take any more data. And last, our adapters have a capability called zero touch for rack level implementations, where you don't need to do anything with the switch settings at all. All of these are IEEE, IETF, and InfiniBand standards compliant and supported by NVIDIA switches and adapters. And for the right two, at least, on the right side of this slide, they're supported by all the major brands as well. Here's a graph showing that with zero touch, there is minimal performance difference between it and other Rocky switch setting on the other switch settings that I showed on the last slide. And this is across all the major, all the message sizes. And it also shows the latency advantage of RDMA over TCP. And more than just latency, the consistency, the consistence of that latency. And this is very important to the CSPs direct advertising business model. They really need consistent latency to make sure that whatever advertisement or the next thing they think you want to see comes at a predictable time, in order for them to ring the cash register with that advertiser. So I've talked a lot about Rocky, the Ethernet version of RDMA, but RDMA is a native protocol on InfiniBand. And like Ethernet, where RDMA runs on, unlike Ethernet, where RDMA runs on top of IP. So you get the highest RDMA performance with InfiniBand on storage or any other application. At NVIDIA, most of our products support both technologies. Now let's look closer at the latency I talked about before and the ramifications to NVMe network storage. Latency is important to storage IOPS performance. This chart shows the latency ramifications by comparing the raw storage latency performance of the storage media to the networked hardware latency. Here is the combined latency of common Ethernet switches and NICs. Here is the latency of NVIDIA Ethernet NICs and switches, which are designed for low latency. Both can run NVMe over fabrics and other storage protocols, but one is designed with the latest, with the latency that's needed for NVMe-based high-performance storage. If we look at InfiniBand, you can see that we have even lower latency. And with common NICs and switches, you have to keep in mind that with common NICs and switches, you're significantly increasing the latency of that data path, especially compared to the performance of SSDs, NVMe-based SSDs in particular. Now look what happens when we add a typical network architecture to the equation. These numbers are multiplied by 3x. And remember that NVMe over Fabrics is a request response protocol, so double that. And if there's speed mismatch and the switches don't support adaptive cut through, so it stores and forwards for speed matching, even more latency is added. So if low latency is important to your network storage solution, pick your networking components carefully. There's one more area we need to address to achieve the performance we need for CSPs, and both Steve and Krill brought this up. We need to help the CPU handle the load requirements that multiple 100 and 200 gigabit storage network ports bring with hardware offloads. This is where the DPU comes into play, the data processing unit. DPUs are designed to offload, accelerate, and isolate data movement like storage. Here are some of the offloads that NVIDIA DPUs can provide for storage networking, which can significantly reduce the load on the server CPU that Steve and Krill were mentioning. Like the GPU, which accelerates compute for the CPU, the DPU accelerates data movement, which is very important to CSP networking storage requirements. But more than that, it adds security to protect that storage from unauthorized access without affecting the performance because of its hardware offload engines for encryption and user isolation, which I'm going to show you in a minute. And DPUs, at least NVIDIA's, have many other storage accelerators like I showed on the last slide. There are many other offloads besides storage and accelerations and accelerator functions on our DPUs, on NVIDIA DPUs, for many other application needs that CSPs also have. But here I'm going to focus only on the storage ones because of the limit of time. Here's how a DPU can accelerate and secure the storage data path. On the left is a traditional server doing software-defined storage, Krill's application basically, with a ConnectX NIC or an HCA. The network adapter provides the data interface, of course, and also can accelerate inline networking functions like the RDMA protocol, TCP checksums, etc. Just general NIC accelerations that have been, baked into them for a long time. But the server CPU is doing the heavy lifting of the storage protocols like NVMe over Fabrics, NFS, security, Krill's Accelero software-defined storage application. All those are running on the CPU. With a DPU, these can all be offloaded from the server. Only user apps remain. And the storage functions are now not only accelerated, but are completely isolated from the user. That means no matter what happens on the server, there is no way for the user to get to storage without authorization from the DPU software, which is not accessible because it's not running on the server's CPU. The DPU can also be used in an all-flash array or JBOF at the other end of the storage data path, as well to accelerate the translation of NVMe protocol to NVMe over Fabric without the need of any general purpose expensive power-hungry CPUs that are typically used today. So how do you program the DPU? The answer is the Doka SOC 4 development kit. It enables developers to rapidly create applications and services on top of DPUs. It leverages industry standard storage APIs like NVMe, VirtIO block, SPDK, etc. Doka is to DPUs what CUDA is to GPUs, an SDK that ensures that applications developed for today's DPUs will also work on tomorrow's. So to summarize, efficient storage networking architectures for CSPs, DPUs to offload, accelerate, and isolate data movement, 100, 200, and soon 400 gigabit Ethernet and InfiniBand low latency networking to move the data, and RDMA protocol to fully take advantage of those fast wire speeds. And with that, I'll turn it back over to Mike.
Thanks, Rob. Let me grab control here and we will go next to the panel questions and audience surveys. So the first panel question we have is, how do you balance scalability, flexibility, performance, and energy footprint in CSP storage and storage networking solutions? We'll start with Steve, and then we'll go to Krill, and then finally with Rob.
Great. Yeah. So I'll start off here. What we hear from our CSP customers is the biggest challenge there is scalability, keeping up with tremendous data growth. And they've really built in flexibility at a software layer, but now how do you take get the most out of the storage that's being deployed, both from just a capacity perspective, right? The raw gigabytes and terabytes needed, and also to maximize the performance. When you do that, really the energy situation, if you can achieve maximum density from both performance and storage, then generally the energy, you're doing the best you can from an energy footprint perspective. And a lot of interest in how do customers use QLC SSTs for broad workloads. Right now, there are just a few companies really deploying QLC, and they either use it for what they call tepid workloads, right? Just a little bit above cool, a little bit warmer than you'd use for a hard drive, or they're spending a lot of money to condition the data to be properly situated, very large sequential operations, everything compressed and deduped right before you write it to the QLC. Those are very expensive operations and tend to reduce the overall value. So it is a challenge right now for companies, but we think with some help from a product like Playaps, then all these can be addressed, right? Get more user data stored to a physical SSD than is actually physically there, as well as use the cheapest possible media. So we're seeing those as being kind of converging trends that are leading to a lot of interest there.
Yeah, and for us, I think that the main component is efficiency on both hardware level, I mean, by passing CPUs to get maximum performance density, and especially on the protocol layer, minimizing data transfer. For example, and the mesh protocol is a client-side protocol, so everything is controlled on the client side, which allows us to reuse some of the bounce buffers, conserving network traffic, conserving usage of remote memory, which both of them really means that the efficiency is improved to almost optimal levels. And we use, and the mesh is architectured for RDMA. So Rob mentioned all the benefits of RDMA networking, and we use it in all our designs.
So just to add to that, as many of you know, Mellanox was acquired by NVIDIA, and the networking business unit that I'm from, of course, was Mellanox. And there at Mellanox, we had a tremendous amount of experience with the CSPs, so have a very scalable, flexible, and high performance, as I've shown, set of products in that area. And because we have all our own IP, excuse me, and so SerDes, which were one of the big power hogs in networking, we design our own. So we were able to keep very tight power budgets on the energy side. But with the acquisition of NVIDIA, we've really come into a whole another level of power energy savings technology because of the graphics cards, of course, that they've been building for years. They've been very focused on that. And that, excuse me again, is enabling us to continue to keep a very low power profile for our networking equipment in future generations as we're able to integrate that technology into our products as well. And then one last thing is the DPUs. So I think that about 30% of CPUs are running those other, the functions like the accelero stacks, the networking stacks, the security, the things I was showing earlier. when you offload those to DPUs, you're now able to have a lower power footprint on your servers, which maybe you can get a lower power CPU. There's lots of ways that DPUs are also going to be saving a lot of energy for data centers.
That's a really good point, Rob. I remember seeing an article somewhere. It said 35% of CPU power utilization is for I/O. So that's definitely makes a big difference. We're going to go to audience survey question number 1. I'll cue this up and let you guys answer it. The question is, what is your organization's greatest concern when using cloud storage? As I said earlier, go ahead and use the Zoom Q&A window. You should see, or the poll window, you should see the questions pop up. And we'll give you a couple minutes to fill that out. And while we do that, we'll go to panel question number 2. And panel question number 2 is, many hyperscalers and CSPs have gone to building their own storage and storage networking hardware over the last decade. What does commercial available technology have to uniquely offer them? We'll start out with Kirill, then go to Rob and finish up with Steve.
Yeah, so I think that closed solutions and hyperscalers all have closed solutions for obvious reasons. Inherently have the other drawbacks. So working with standard protocols actually allows hyperscalers to absorb new ideas coming from startups or coming from other places. This is why I think that we see more and more exposure of standard interfaces during last years, from instances with NVMe drives to opening some of the underlying networking in AWS with libfabric, and availability of standard RDMA instances, especially for HPC and GPU computing in Azure. So I think that this trend will continue and will allow both hyperscalers themselves and application owners deploying on public clouds to make use of additional technologies like NVMe.
So I think that doing everything yourself is a pendulum in our industry, like many other pendulums in our industry that swings back and forth. I'm pretty old, and when I was, young in my high school and college days, there was something called mainframe computers, and IBM was the leader in mainframe computers, and they even sold you the paper that went into the printers and everything else, from the desktop green screens all the way through the entire system. And that pendulum, of course, with workstations, Apollo Sun workstations, totally switched to the other direction. And then of course there was the PC servers, et cetera, et cetera. And as the hyperscalers got bigger and bigger, I think they sort of moved back to that even the paper area of thinking. But I think Kirill said it perfectly. The problem is when you're a closed system, you are focused on other things than the whole industry focuses on. So the innovation of the whole industry is what you're able to get by, using that innovation in your systems that comes from the startups and all the different vendors that are competing to try to get the best solutions.
Yeah, I totally agree with everything Rob and Kirill said. Another perspective is, these are in many cases trillion-dollar companies. Trillion-dollar companies can do kind of whatever they like, but even there they need to be selective, right? They don't want to recreate an entire industry. They want to leverage the industry, and they're going to be selective in where they choose to innovate internally. I'd say the other thing that even $1 trillion doesn't buy you is a time machine. So, there's a lot of startups, a lot of large companies, a lot of small companies that are investing ahead of where these large CSPs are. And if somebody decides to build something similar on their own, then they're going to be waiting years and years to enjoy the benefits and spending hundreds of millions more in infrastructure that they don't need to by waiting for an internal solution. So I do think you're going to see companies innovate internally, but they're absolutely going to have to use what's available, the best of breed that's available in the market. And that's obviously true. If you're not a $1 trillion company, then you can't necessarily build your own semiconductor products or distributed storage products, and you need to leverage the best of breed that's available in the market.
In high tech, history repeats itself, and that pendulum is starting to swing the other way.
Absolutely. Yep. Absolutely.
Very true. Very true. All right, let's go to audience survey question number 2. And this question is, when building a cloud data center storage infrastructure, what is your greatest concern? I'll launch that poll. And again, give you a couple minutes to fill that out while we go to panel question number 3. And that question is, many CSPs and hyperscalers now offer cloud-based instances of open technologies, such as NVMe, NVMe over Fabric, and clustered file systems. What is the best way to integrate these technologies into their storage architectures? We'll start with Rob, and then go to Steve, and then finish up with Kirill.
I think that Accelero is a perfect example of that. There's hyperscalers, and one that they're working closely with that have added what they call HPC in the cloud, and they have InfiniBand networks that they then rent these supercomputers they built to users, just like they rent VMs. And Accelero has their solution integrated into their HPC in the cloud solution, which is a perfect example of what you're talking about here. And I think that we have many other storage partners and customers that are also working on solutions or have solutions that fit this model.
Right. Kind of building on top of that, right? You have these amazing fast technologies, NVMe, NVMe-OF. You have clustered file systems, various distributed, software-defined storage layers. And really the key is, how do you take advantage of those very fast technologies, make sure your local node is keeping up with that from a performance perspective, number one. Number two, how do you get the most efficiency, meaning the most density from that node? That's going to improve costs, improve power consumption. But then everyone worries about blast radius. If I put too much data in one node, what happens if it goes down? Right? They have means of protecting from that, but they want to balance that. Making that local node more reliable means they can scale more efficiently, have less overhead at the node level. So, fewer redundant nodes, and still achieve the same type of end user SLA, reliability SLAs that they're responsible for.
Yeah, and I think that since these technologies are very open and there is a lot of materials, so it looks simple, but actually it isn't, especially at scale. And NVMe drives become larger, and so applications can't efficiently use the whole drive anymore. And there is no simple way to consume protected volumes based just on NVMe and NVMe or fabrics. So people try all kinds of scripting environments, but when it comes to scale, and CSPs, as we already discussed, it operate at scale, it can't operate at production grade. So this is actually, as mirroring what Rob said, this is actually where some of the larger customers came to us. To really create something that both based on open source, on open technologies, and something that can work at scale.
Excellent. Well, thank you guys. Q&A, we only have one question. That one already got answered. So I think that wraps it up. Again, thank you for attending our webinar. We will make a link to the recording available to everybody who registered, as well as a PDF of the slide set. Again, thank you, Kirill, Rob, and Steve for sponsoring this webinar, and we really appreciate your guys' viewpoints, and I thought this was really excellent.
You're very welcome, Mike.
Yeah, you're welcome, Mike. Thank you for your hosting.
Thank you, everybody. Have a great day.
You too.